Yeah, so you see the screen? Okay. So the topic of my talk was vapor flow optimization by means of coherent beam combining with the Civan laser and beam shaping strategies to reduce spatter in laser welding. Yeah, so in deep penetration welding processes, we typically have an increase in spatter formation at increasing welding speeds. And of course, you do not want to have any spatter because they land on optics and parts. And also with the loss of material, you have a reduction of bonding area, which reduces the mechanical properties. And to have a better understanding and of what causes a spatter formation, I showed here a high-speed synchrotron recording of a deep penetration welding process. We see the laser beam hitting the sample surface, creating the capillary. And here in the back, you can see the melt pool. And with tracer particles, you can see the direction of the flows in the melt pool. And so for spatter to occur, basically one flow of a melt particle in an upward direction is required. So then a spatter can, or this particle can overcome the surface tension. And this is caused, so this upward direction is caused mainly by two things, which is the melt flow itself. So if you got turbulences and eddies in the melt flow or in the melt pool behind the capillary, or from outflowing vapor flow. So inside the capillary is pressure to keep this capillary open, and this vapor is then flowing outward in an upward direction. And with interaction with the melt, it accelerates the melt in an upward direction. So here I pointed it out again. And so to influence the formation of spatter, we can basically change the dynamics of the melt flow. We can change the vapor flow direction and velocity, and both of it is connected to the shape of the capillary. And in literature, or what we can find on the market at the moment, is other beam shaping strategies to address this issue. So here with the well-known core ring systems on the market, or since ages mainly, we can see here the influence of such systems on the shape of the capillary. Here different core ring power distributions are displayed in the shape of the capillary. And especially at 16-70% of laser power in the core, we can see a great impact on the capillary, at least at the aperture. And with such systems, we can see here the core-only mode with a quite narrow capillary, and we see a lot of spatter. And when we change it to another power distribution between core and ring, we can see an at least wider capillary opening and a total reduction of spatter formation. So here on the right, you can see the graph, which shows the number of spatters, and with the core ring intensity distribution, we can greatly reduce spatter formation. Yeah, so another approach is the use of a second laser source, which in this case was a diode laser. We then pointed it at an angle on the sample surface. And here on the bottom, you can see then a welding process with the reference, so without the diode laser. And you can see here this fluctuating capillary back wall and this ejection of melt resulting in spatter formation. If we then here apply the diode laser, we see a great change in the shape of the capillary and a change of the capillary back wall behavior. And if I record it again, you can see that from the backside of the capillary, basically no spatter occurred. However, now we have other effects, but the main issue here was to reduce the spatter formation from the backside of the capillary. So with these well-known systems, we can directly change the capillary aperture, so the shape of the capillary also, and also then the direction of vapor So the vapor is not directing directly on the capillary back wall anymore, but more or less in a more open way. However, these systems have limits in their flexibility, so there are not as many core ring dimensions or ratios if you can choose from. And with the second laser beam, you have a lot of adjustment effort. So it's a real pain to superimpose these two beams. So this is why novel beam shaping technologies are required to really address these issues for all the different welding situations we have. And I probably can skip this. So then I explain typically how the Civan laser works. We can get this average fluence. We say switch times below 100 nanoseconds. And we use then the Civan laser to create an optimized beam shape, as we called it, to address these issues which are directed to spatter formation or vice versa. We learned from the results from the past with the other systems that we want to create a capillary aperture to change the direction of vapor. So we designed with the system a beam shape to address this. So here, this is the beam shape basically. On top, you can see how the different spots are addressed. And on the bottom, you can see the average fluence image. And here with the side maxima, we actually used it to increase the capillary aperture in longitudinal direction, so in welding direction. And this second one as well to also get like this opening of the capillary. And then we compare it to the single spot, single point, however you call it, but this is just the main intensity peak in the center. This was the experimental setup of the IFSW. So we were welding stainless steel AC304 at 12 meters per minute, and we set a capillary depth of 1.5 millimeters. We then used our X-ray imaging system, which consists of an X-ray tube that emits X-rays which penetrate through the sample. So we are welding perpendicular to the X-ray beam. So the beams are then attenuated based on the local density. And these beams hit a scintillator that converts the X-ray beams into visible light. And then we have an imaging system with an image intensifier to record the process, basically. Here on the top, you can see such an X-ray recording. And by averaging the frames, we get the time averaged capillary. So here you can see the contour of the capillary. So now when we have a look at the different contours, we see on the left-hand side the reference beam, so just a single spot, and on the right-hand side the optimized beam shape. And we can even see here greatly the influence of the beam shape. On the left, it's quite narrow capillary opening compared to the optimized beam shape, which is more stretched in the welding direction, which is to the right. So we now have the X-ray recordings, and from these we then get an information based on the gray values or the pixel values of the cavity. So with these informations, we can then three-dimensionally reconstruct the shape of the capillary, which is what we do since, I guess, 2017. And then we can investigate the vapor flow out of the reconstructed capillary, which was the goal of this research here. So now with the reconstructed capillary, we applied ray tracing. So we used the ray tracer from our Professor Michalowski, which was here as a PhD student already. And we can then determine the absorbed irradiance on the inner wall of the capillary. And with this information, we can then process it to calculate the temperature on the capillary inner wall. And with that, we can calculate the vapor velocity of the inner wall. into the cavity of the capillary. And even here we can see that we have velocities of the vapor from the surface at 290 meters per second. So with this information, we then did a simulation in open foam. So we just have a vapor simulation, and we can see here for the reference beam that we have a vapor flow in a quite upward direction. So we can see here that the vapor has a great potential to accelerate the melt here on the capillary backside into the upward direction. And if we compare it to the optimized beam shape, we can see that we have different directions of vapor, and especially so that here the change is that we do not have such an acceleration of melt in an upward direction, more in an angled way, basically. So at last, we then investigated the influence on the formation of spatter. Here on the top, you can see the superimposed images, so the max intensity image with quite a lot of spatter. And here on the right-hand side with the optimized beam shape, we can see that we reduced the formation of spatter with this beam shape. And in total, it was a reduction of 85% at welding speeds of 12 meters per minute. So with beam shaping, we can then optimize the vapor flow to then reduce the formation of spatter. So yeah, that was it from my side, and this was all the talk I held at Japan and in Munich. Yeah, that's it.